Hello, friend. Tonight, we're going to drift gently into the quiet science behind one of the most calming sights the Earth has ever created, the Northern Lights. These soft arcs of color rise and fall in the sky like slow-motion waves, glowing in shades of green, pink, and deep red as they trace the shape of Earth's magnetic field. People have watched them for thousands of years, sometimes with wonder, sometimes with fear, sometimes with the feeling that something beyond the ordinary was brushing lightly across the night. But the real explanation, rooted in physics and the calm structure of our planet, is far more soothing than mysterious. The glow of an aurora begins far from Earth, carried toward us on streams of particles that leave the sun in steady flows. When these particles reach the Earth, they are guided toward the poles by the magnetic field, gliding along invisible pathways that lead them into the upper atmosphere. There, they meet oxygen and nitrogen atoms, releasing gentle bursts of light. Each color, each ripple, and each faint shimmer has its own story. Tonight, we'll explore those stories slowly and comfortably. What shapes the lights, why they appear where they do, how altitude changes their color, and why some auroras drift like curtains while others twist into spirals or silent pulses. Before we move any deeper, if these long, calming sessions help you unwind or fall asleep, you're welcome to subscribe so new videos find you easily. And if you'd like to share a topic that settles your thoughts or sparks your curiosity, you can leave a comment as well. It's always meaningful to hear what brings you comfort at the end of the day. Now that you're settling in, you can allow your breathing to soften and let the imagery shape itself gently in your mind. You don't need to follow every detail. You can simply rest with the quietness of the topic, letting the soft glow of the aurora drift across your imagination. The Northern Lights begin with something simple: particles traveling through space. These particles come from the sun, carried outward in a steady stream known as the solar wind. Most of the time, the solar wind drifts past Earth without much effect, gliding around the planet as it moves through space. But some of those particles become captured by Earth's magnetic field, guided toward the far north and far south where the field lines bend inward. The aurora is the quiet interaction between those particles and the thin upper layers of our atmosphere. High above the surface, far above clouds, mountains, and even the flight paths of airplanes, the atmosphere becomes incredibly delicate. This region is filled with oxygen atoms, nitrogen molecules, and a scattering of other gases spread across vast distances. When particles from the sun reach this rarefied layer, they collide gently with those atoms and molecules. These collisions transfer energy, lifting electrons into more excited states. When the electrons return to their normal positions, they release that extra energy as small bursts of light. Millions of these microscopic glows occur at once, combining to create the sweeping shapes we see from the ground. Each type of gas produces its own signature glow. Oxygen can release a soft green or, at higher altitudes, a deep red. Nitrogen creates blues and purples, shaping the edges of the aurora and giving some displays their subtle multicolored fringes. The colors we see depend on which gases the incoming particles encounter, how much energy they carry, and how high in the atmosphere the collision takes place. The lights are not a single blanket of color, but a layered expression of different reactions happening at slightly different elevations. The shapes of the aurora are guided by Earth's magnetic field, which is constantly curving and arching as it flows outward from the planet. When particles follow those invisible lines, the light they create maps the magnetic structure above our heads. Curtains form where the particles descend in slender sheets. Spirals appear when the field lines twist. Pulses and patches form when energy arrives in uneven bursts. Some displays drift gently, while others ripple in quick, delicate motions that last only a few seconds before fading. All of it reflects the same quiet principle. The lights reveal the shape of a magnetic field we cannot otherwise see. Even though the aurora can look intense or dramatic, the actual collisions that produce the glow are small and subtle. They take place across vast regions of sky, spread over hundreds of kilometers in height. The brightness comes from the sheer number of interactions happening at once, each releasing just a tiny glimmer of light. The result is a natural display, built entirely from countless microscopic events, layered together until they create something large enough to paint the night. Understanding these details doesn't make the aurora any less beautiful. If anything, it reveals how gentle the phenomenon truly is. A calm interplay between sunlight, magnetism, and the thin upper air above our world. A display shaped by physics, yet soft enough to feel almost like a dream forming along the edges of the sky. And even though the science is precise, it unfolds in a way that encourages the mind to settle, as if the lights themselves were designed to quiet thought and ease the space around you. The northern lights begin their journey on the surface of the sun, in regions where hot plasma rises and falls in slow, churning motions. The sun is constantly releasing a stream of charged particles into space, a flow known as the solar wind. This wind is not like air moving across Earth. It is a scattering of electrons and protons drifting outward in every direction, expanding through the solar system in a steady, continuous wave. Even though it spreads across enormous distances, by the time it reaches Earth, the solar wind is gentle, thin enough that its particles pass between planets without making any sound or pressure we could feel. These particles come from the sun's outer atmosphere, a layer called the corona. The corona is extremely hot, far hotter than the visible surface beneath it, and that heat gives the particles enough energy to escape the sun's gravity. Once released, the solar wind travels through space at hundreds of kilometers per second. The speed can change depending on the sun's activity. Calm periods send a lighter stream. Active periods, marked by sunspots or magnetic disturbances, can release faster, denser bursts of particles. These stronger flows are the ones most likely to enhance the aurora, adding brightness and movement to displays near the poles. When the solar wind reaches Earth, it meets the planet's magnetic field long before it reaches the atmosphere. The field deflects most of the particles, guiding them around the Earth and forming a protective boundary called the magnetopause. Only a fraction of the particles make it inside, slipping through regions where the field lines open or reconnect. These entry points are typically near the poles, where the magnetic field funnels inward. Without this magnetic guidance, the solar wind would simply drift past us, unnoticed. Instead, the field shapes the path of the particles, creating the conditions necessary for the northern lights to appear. The solar wind is not constant. It changes with the sun's rhythms, which rise and fall over an 11-year cycle. During solar maximum, sunspots become more common, and the sun releases more energetic particles. Stronger winds create more frequent and more vivid auroras, sometimes pushing the lights farther from the poles. During solar minimum, the sun quiets. and the auroras retreat toward the Arctic and Antarctic regions. These cycles mean that some years are naturally more active than others, giving the sky its own long-term pattern of brightness and calm. Embedded within the solar wind are magnetic fields carried outward from the sun. These fields twist and stretch as they travel, interacting with Earth's magnetic field when they meet. The direction of the solar magnetic field matters. When it aligns in certain ways, it connects more easily with Earth's field, allowing a greater flow of particles into the magnetosphere. These quiet alignments can suddenly increase auroral activity, creating nights when the lights move with more energy than usual. Despite all this motion, the solar wind feels peaceful when imagined from a distance. Particles leaving the sun in a continuous stream, drifting across empty space, and eventually meeting Earth in a delicate interaction that produces light. It is a reminder that the northern lights begin not with anything violent or loud, but with a steady, gentle outflow from our star. A quiet contribution from the sun, traveling across millions of kilometers before softly illuminating the sky. Surrounding the Earth is an invisible structure shaped entirely by magnetism. This structure, called the magnetosphere, forms a protective bubble that stretches far into space. It is created by motions within Earth's liquid outer core, where swirling metal generates the magnetic field that extends outward from the planet. The magnetosphere bends, curves, and flows in response to the solar wind, shaping itself into a long teardrop, with a rounded side facing the sun and a long tail stretching away into the dark. Though no one can see it directly, the magnetosphere guides nearly every part of the aurora's behavior. As the solar wind approaches Earth, most of its charged particles are deflected by this magnetic barrier. The magnetic field pushes against the incoming flow, slowing it and forcing it to slide around the planet instead of hitting the atmosphere head-on. This protective effect is essential. Without it, the solar wind would strip away the upper layers of the atmosphere over time. Instead, the magnetosphere absorbs the pressure and channels only a small portion of particles into narrow regions near the poles where the field lines curve inward. These entry zones are the quiet gateways through which auroral particles begin their descent. Within the magnetosphere, the magnetic field lines act like paths that guide charged particles along precise routes. When particles from the solar wind become trapped in this region, they begin to spiral along these lines, drifting toward the poles with increasing speed. The magnetosphere's shape ensures that particles do not spread evenly around the planet, but instead concentrate into two glowing rings, known as the auroral ovals, one around the Arctic and one around Antarctica. These ovals mark the regions where the aurora is most likely to form, matching the exact shape of the magnetic field high above the surface. The magnetosphere is not static. It flexes and reshapes itself constantly in response to changes in the solar wind. When the wind strengthens, the outer boundary compresses. When it weakens, the boundary expands outward again. These motions happen quietly and continuously. Farther behind the Earth, in the magnetotail, the magnetic field lines stretch until they eventually reconnect, releasing stored energy. This reconnection process allows fresh bursts of particles to stream toward the poles, brightening the aurora or setting the stage for a more active display. Though these processes are large in scale, they unfold smoothly, forming the calm background rhythm of auroral activity. Measurements from satellites have shown that the magnetosphere acts almost like a filter. Only certain particles, following certain paths, will eventually reach the atmosphere. Many others are deflected or trapped temporarily before drifting away. The aurora is created by the small percentage that move along the right field lines and descend into the thin upper air. Without the magnetosphere to organize this motion, the northern lights would not form the graceful shapes we see from the ground. Instead of arcs and curtains, the sky would fill with scattered glimmers, lacking the structure that magnetism provides. This invisible shield also protects living things on Earth from harmful solar radiation. While the aurora expresses the beauty of this interaction, the magnetosphere expresses the function, quietly shielding the surface from charged particles that would otherwise reach the atmosphere in greater numbers. It holds the space around Earth in a structured balance, allowing only a controlled trickle of particles to slip in along specific magnetic routes. In imagining the magnetosphere, it becomes easier to picture the northern lights not as isolated streaks in the sky, but as the visible edge of a much larger process. A protective bubble shaping the arrival of particles, guiding them toward the poles, and outlining the soft ribbons of light that appear high above the world. A silent structure, immense yet gentle, forming the unseen framework of every auroral glow. Even though the solar wind surrounds Earth on all sides, the northern lights appear most often in the Arctic and Antarctic regions. This pattern comes from the way Earth's magnetic field directs the flow of charged particles. The field isn't arranged like a simple sphere. Instead, it bends inward near the poles, forming narrow funnels where magnetic lines converge. These converging lines act as entry points, guiding particles from the solar wind into the atmosphere high above the polar regions. Because of this structure, auroras naturally form circles of light around each pole rather than spreading evenly across the planet. These circles are known as the auroral ovals. They are not fixed in place but shift and stretch depending on the strength of the solar wind. On calm nights, the ovals contract inward, staying close to the polar regions. During stronger solar activity, they expand, sometimes reaching latitudes far from their usual boundaries. This expansion explains why people living in northern Europe, central Canada, or even the northern United States occasionally see the aurora during particularly active periods. The positions of the ovals are a constant reflection of the balance between Earth's magnetic field and the incoming flow of charged particles. The reason the poles function as gateways lies in the geometry of the magnetic field. At the equator, magnetic lines run parallel to Earth's surface, providing little downward guidance. Particles following these lines are held above the atmosphere, drifting along paths that circle the planet. Near the poles, however, the lines tilt sharply downward. As particles spiral along them, they are naturally drawn into the upper atmosphere. The descent is gradual and guided, creating the long curtains of color that sweep across the sky. Without this funneling effect, the particles would never reach the atmospheric layers where the aurora is created. Earth's magnetic poles are not the same as its geographic poles. The magnetic poles drift over time due to ongoing changes in the flow of molten metal within the core. This drift slightly alters the position of the auroral ovals from year to year. Satellite observations show that these movements are subtle but continuous. giving the ovals a slow, wandering quality. Despite this motion, the auroras remain closely tied to the high latitudes because the overall magnetic structure remains stable on human timescales. Another factor contributing to polar auroras is the shape of the magnetosphere itself. When the solar wind strikes the magnetosphere, it compresses the sun-facing side and stretches the opposite side into a long tail. Reconnection events in this tail send bursts of energy toward Earth along magnetic field lines that lead directly to the poles. These bursts create the more active forms of the aurora, ripples, spirals, and sudden brightening. The tail acts as a reservoir of energy, storing and releasing magnetic tension in a way that enhances auroras only where the field lines converge downward. Although auroras do exist far from the poles under rare conditions, those events require unusually strong solar storms. During such storms, the magnetic field becomes more open, allowing particles to enter along lines that normally do not connect with the atmosphere. These lower latitude auroras are brief and unpredictable. For the vast majority of nights, the lights remain anchored to the regions near the poles, forming reliable rings of activity that circle the Arctic and Antarctic landscapes. Understanding why auroras gather near the poles transforms the phenomenon from a random sky display into something structured and predictable. The lights reveal the shape of Earth's magnetic field, outlining its curves and guiding the movement of particles through space. In their soft glow, the invisible becomes visible, turning the polar sky into a gentle expression of the forces protecting and shaping our world. Auroras rarely appear as simple patches of light. Instead, they take on shapes that look almost architectural. Long curtains that hang across the sky, sweeping arcs that bend from horizon to horizon, and spirals that twist gently in the darkness. These shapes form because the aurora is not just a glow, it is a glowing map of Earth's magnetic field. The charged particles illuminating the sky follow specific magnetic pathways, and those pathways determine the structure of the light. The most common auroral form is the curtain. Curtains develop when particles descend along nearly parallel magnetic field lines. Each line carries its own stream of particles, and when many streams descend side by side, they create vertical sheets of light. These sheets can stretch for hundreds of kilometers, forming tall, quiet walls that ripple softly as the flow of particles changes. From the ground, they appear almost draped across the sky, like long folds of fabric glowing in still air. Sometimes these curtains bend into arcs. Arcs form when the magnetic field lines curve as they approach the atmosphere, guiding the particles into smooth, sweeping shapes. These arcs are often the first sign that an aurora is forming. They begin as thin, faint lines and slowly brighten as more particles enter the atmosphere. The curvature reflects the shape of the magnetic field above the Earth, revealing the invisible structure that surrounds the planet. More active displays can take the shape of spirals or helices. These patterns occur when disturbances in the magnetosphere cause the field lines to twist. As particles travel along these twisted paths, the resulting glow follows the same motion, creating rotating formations that appear to unwind across the sky. Although they look dynamic, the movements are usually gentle, unfolding slowly enough to feel calm and steady. Another form, known as a rayed curtain, appears when fine structures develop within a larger sheet. These rays are thin columns of light, formed by slight differences in the density or direction of incoming particles. When viewed from below, the rays appear like vertical beams stretching upward into the sky. When seen from the side, they merge into the larger curtain around them. This shift in perspective explains why auroras can appear different depending on the angle from which they're viewed. A less common but striking pattern is the corona. Coronas occur when an aurora forms directly overhead, and the magnetic field lines point downward toward the observer. The light appears to radiate outward from a single point, creating the illusion of a spreading burst or star-shaped formation. Though dramatic, coronas are quiet processes, simply the geometric result of looking directly along the paths of descending particles. Ripples and waves within auroral formations come from small fluctuations in the magnetosphere. As the solar wind interacts with Earth's magnetic field, it creates particle flows that strengthen and weaken in subtle cycles. These variations cause the aurora to pulse, brighten, or shift in shape. Even the fastest movements, the ones that shimmer briefly across the sky, come from changes in the flow of particles along magnetic pathways rather than turbulence in the atmosphere. Auroras can also form broad, diffuse glows with no clear structure. These displays happen when particles enter the atmosphere across a wide area rather than along tightly organized field lines. The result is a soft, featureless brightness that can fill the sky without forming distinct patterns. Although less dramatic, these glows are still guided by magnetism. They simply reflect a more even distribution of incoming particles. By understanding these shapes, the aurora becomes easier to read. Each form traces a different aspect of Earth's magnetic environment. Curtains show parallel field lines, arcs show curvature, spirals reveal twisting motions, and coronas mark the locations where magnetic lines point straight downward. What we see from the ground is the glow that outlines these invisible structures, turning the sky into a quiet rendering of the magnetosphere above. The colors of the northern lights are shaped quietly by height. High above the ground, the atmosphere becomes thinner and more delicate, and the gases there respond differently when struck by charged particles. As these particles descend along magnetic field lines, they encounter different layers of oxygen and nitrogen at different altitudes. Each layer produces a distinct glow, creating the vertical color structure that gives the aurora its soft, shifting palette. At higher altitudes, where the atmosphere stretches into the lower edge of space, oxygen atoms are sparse but highly energetic. When particles from the solar wind collide with them here, the oxygen releases a faint, deep red light. This red glow forms above most other auroral colors and can reach heights of more than 300 kilometers. Because these regions are thin and collisions are less frequent, the red emissions develop slowly and appear as gentle, diffuse glows. On quiet nights, they hang like faint veils above the brighter layers below. Lower in the atmosphere, between roughly 100 and 200 kilometers, oxygen produces the green light most people associate with the aurora. This range contains the highest number of oxygen atoms that are still sparse enough for collisions to produce long-lasting glows. Green emissions occur when excited oxygen atoms release energy after being struck by incoming particles. The process is efficient and frequent, making green the most visible and persistent color in most auroral displays. It often forms the base of curtains and arcs, outlining the shapes guided by the magnetic field. nitrogen contributes additional colors. At similar altitudes where green auroras form, nitrogen molecules can produce a blue-violet glow when energized. The color is less noticeable from the ground because it forms lower and fades more quickly, especially under city lights or moonlit skies. At slightly higher altitudes, nitrogen ions can create purples and pinks, particularly along the lower edges of bright curtains, where collisions happen at a faster pace. These subtle tones sometimes trace the underside of green formations, adding delicate layers that shift with each change in particle flow. The altitude also influences how bright each color appears. In the thinner upper layers, where densities are low, particles can travel longer distances before colliding with gas molecules. This allows for red emissions, which require more time before releasing light. At mid-level altitudes, where densities increase, collisions happen more frequently, producing the vivid greens and blues that ripple through most displays. Lower altitudes, below roughly 100 kilometers, allow nitrogen to glow with deeper violet tones, although these colors are rarely bright enough to dominate the sky. Temperature and atmospheric composition also play a role. During colder months, the upper atmosphere contracts slightly, shifting the regions where collisions occur. Solar activity affects color as well. Stronger bursts of particles can energize gases at lower altitudes, introducing colors that are otherwise too faint to notice. These variations mean that each aurora carries its own quiet pattern of color, depending on the conditions at the time. The layering of colors creates the impression that the aurora is stacked vertically, with faint red above, bright green in the middle, and blue or purple along the lower edges. This vertical arrangement matches the structure of the atmosphere itself. As the particles descend, they trace the changing density of gases, leaving behind glows that shift from warm to cool tones in a smooth gradient. Even the motion of the aurora can reflect altitude, with higher red regions drifting more slowly than the lively green formations beneath them. By understanding how altitude shapes color, the aurora becomes more than a display of light. It becomes a cross-section of the atmosphere, quietly showing the layers of oxygen and nitrogen that surround the Earth. Each color is a marker of height, a sign of which atoms were energized and how they returned that energy to the sky. Together, they create the soft spectrum that makes the northern lights so distinctive, balanced in gentle transitions from one hue to the next. Among all the colors in an auroral display, green appears most often. It sweeps across the sky in long curtains, outlines arcs from horizon to horizon, and forms the base layer of many multicolored auroras. The reason for its dominance comes from a combination of atmospheric chemistry, altitude, and the way oxygen atoms release light after being struck by particles from the sun. The balance of these factors makes green the easiest color to produce and the one most visible to the human eye. Green auroras are created by oxygen atoms located roughly 100 to 150 kilometers above the Earth. This region of the atmosphere holds the ideal density for the process that creates green light. There are enough oxygen atoms for frequent collisions with charged particles, but not so many that the excited atoms are disrupted before emitting light. When an incoming electron strikes an oxygen atom here, it lifts one of its electrons into a higher energy state. When the atom relaxes back to normal, it releases a photon, a small packet of green light with a wavelength of 557.7 nanometers. This specific wavelength is responsible for the classic emerald glow. Another reason green is common is that the energy threshold needed to produce it aligns closely with the energy of particles arriving from the solar wind. Many of the electrons funneled into the atmosphere have just the right amount of energy to excite oxygen atoms at these altitudes. As a result, even modest solar activity can create strong green emissions. In contrast, the deep red auroras that form at higher altitudes require more specific conditions, and the blue or purple emissions from nitrogen form lower in the atmosphere, where they can be harder to see. Green light is also more visible to human eyes, especially at night. Our night vision is guided by cells in the retina that are more sensitive to green and yellow wavelengths than to blues or reds. This means that even when multiple auroral colors are present, the green stands out the most. In darkness, the human eye struggles to distinguish subtle reds or faint purples, but green remains clear and easily perceived. This natural sensitivity helps the green aurora appear brighter and more prominent than other colors, even if they are occurring at similar intensities. The altitude where green auroras form also makes them more stable than other colors. Red emissions occur hundreds of kilometers above the ground, where collisions are infrequent, and the glow spreads across wide areas, making it diffuse and faint. Blue and violet emissions from nitrogen occur much lower, closer to the denser atmosphere, where they fade quickly due to rapid collisions. Green sits in the middle, high enough to avoid rapid quenching, but low enough for strong, frequent emissions. This balance allows green auroras to persist for long periods and ripple smoothly along magnetic field lines. Solar activity can enhance these greens further. During times of increased solar wind or minor geomagnetic disturbances, more particles reach the oxygen-rich regions where green auroras form. The increased flow brightens the color, creates sharper structures, and adds motion to the curtains and arcs. Even during these active periods, green remains the dominant hue because the fundamental conditions favor its creation. In some auroral displays, other colors appear alongside the green. The upper edges may shift into red, while the lower edges trace faint blues or purples. These layered colors reveal the vertical structure of the atmosphere and the changing energies of the particles entering it. Yet in most conditions, the green region outshines the others, forming the familiar glow that people recognize around the world. By understanding why green is so common, the aurora becomes easier to interpret. It reflects not just the behavior of particles, but the composition and structure of our atmosphere. The green glow is the most visible expression of oxygen's quiet response to energy arriving from space, a steady and reliable signature of the interactions occurring high above the Earth. And while every aurora is unique, the soft green light remains its most constant and comforting presence. Although green dominates most auroral displays, other colors appear under specific conditions. These rarer hues form at different heights in the atmosphere, where gases behave differently when struck by energetic particles. The combination of altitude, particle energy, and atmospheric density determines whether an aurora glows red, blue, purple, or pink. Each of these colors offers a quiet hint about what is happening high above the Earth. Red auroras form at the greatest heights, often above 200 kilometers. At this altitude, the atmosphere is extremely thin, and oxygen atoms are spaced far apart. When charged particles excite these oxygen atoms, the atoms release light very slowly. If another atom strikes them before they can emit light, the glow disappears. Because collisions are rare at such heights, the red emission survives long enough to be visible. The result is a soft, diffuse red layer that hangs above the brighter green aurora. Red auroras often appear during strong solar activity, when the flow of particles is intense enough to reach these high altitudes. Blue auroras come from interactions with nitrogen molecules at lower altitudes, typically below 100 kilometers. In this denser region, deeper collisions occur, and nitrogen releases photons in the blue part of the spectrum. Blue auroras can be vivid, but they fade quickly because the lower atmosphere contains more molecules that quench the glow through rapid collisions. Moonlight, city lights, and atmospheric haze can also reduce visibility. As a result, bright blue auroras are rarely seen from areas with much ambient light. Purple and violet auroras form when emissions from nitrogen overlap with emissions from oxygen. These colors typically appear along the lower fringes of active auroral curtains, where incoming particles carry enough energy to reach denser regions of the atmosphere. The mix of nitrogen's blue light and oxygen's red light creates a range of purples that shift with the particle flow. These hues can appear briefly during sudden bursts of energy, known as auroral substorms, or during the edges of rapidly moving structures. Pink auroras are a blend of red and blue emissions. They occur when energetic particles penetrate deeper than usual, exciting nitrogen at low altitudes, while oxygen at slightly higher altitudes produces red light. When the two emissions overlap, the resulting glow appears pink. This color tends to show up during strong displays, especially along the lower edges of bright curtains where the particle energy changes quickly. The specific color of an aurora depends not only on altitude and gas type, but also on the energy of the incoming particles. Lower energy particles interact higher in the atmosphere, producing red emissions. Higher energy particles travel farther downward, creating greens, blues, and purples. Some displays shift color as the energy of the particles varies from moment to moment. A curtain may appear green at first, then glow faintly red at its upper edge, and finally develop purple fringes as the activity strengthens. Rare colors often reveal the structure of the atmosphere itself. Red auroras mark the thin, expansive upper layers. Green marks the oxygen-rich mid-altitudes. Blue and purple trace the denser regions lower down. Together, they form a vertical gradient of light that mirrors how air thins with height. Because the conditions for producing these colors are so specific, they appear less frequently and often for shorter durations. Yet when they do appear, they add depth to the aurora, showing the complex and layered nature of the interaction between solar particles and atmospheric gases. These rare hues remind observers that even within a familiar phenomenon, subtle variations can create unexpectedly beautiful forms. A quiet interplay of energy and chemistry unfolding above the world. From the ground, auroras can appear almost alive, shifting in ways that seem both gentle and unpredictable. Some displays drift quietly across the sky, moving so slowly that their changes can be missed unless watched closely. Others ripple, brighten, or twist in sudden bursts of motion. Even though these movements look fluid, they are guided by the hidden structure of Earth's magnetic field and by fluctuations in the stream of particles arriving from space. Understanding these motions begins with recognizing that auroras do not move through the air. They move along magnetic pathways far above the atmosphere. The patterns we see on the ground reflect how charged particles slide along magnetic field lines. When the flow of particles increases, a curtain of light might brighten or widen. When the flow weakens, the same curtain fades. These changes can occur gradually over minutes or develop in quick pulses lasting only a few seconds. The movement is not caused by wind or turbulence. Instead, it is the result of shifting currents of particles traveling through the magnetosphere and into the upper atmosphere. Auroras can drift laterally across the sky when the magnetic field lines guiding them shift in shape. The magnetosphere is constantly adjusting to changes in the solar wind. If the solar wind strengthens, it compresses the front of the magnetosphere and alters the alignment of the field lines. This subtle adjustment can cause the auroral oval to move slightly, making arcs or bands of light drift across the horizon. These motions are slow and broad, giving the aurora a steady, gliding quality. Faster motions occur during processes known as auroral substorms. In the distant magnetotail behind Earth, magnetic field lines stretch and store energy. When these lines snap back into a new configuration, they release energy that accelerates particles toward the poles. The sudden increase in particle flow creates rapid changes in brightness and shape. Curtains can fold into spirals, arcs can break into separate rays, and faint glows can erupt into vivid formations. Despite their dramatic appearance, substorms unfold in a controlled and predictable way, shaped by the physics of magnetic reconnection. The vertical motion seen in some auroras is an illusion created by changing brightness at different altitudes. When incoming particles fluctuate in energy, they excite different layers of the atmosphere. Sometimes the higher red-producing regions brighten first. Other times the lower nitrogen-rich layers respond more strongly. These changes can give the impression that the aurora is rising or falling, even though the structure remains anchored to the same magnetic pathways. The speed of auroral motion depends heavily on the energy of the particles entering the atmosphere. High-energy particles move more quickly along magnetic field lines and can create rapid, shimmering effects. Lower-energy particles produce slower, more diffuse glows. The overall activity level of the sun also plays a role. During solar maximum, when the solar wind is more active, auroras tend to move more energetically and appear more frequently. During quieter periods, their motions are softer and more subtle. Distance also affects how motion appears. Auroras occur tens to hundreds of kilometers above the ground. At that scale, even rapid changes can appear slow from below. A brightening that sweeps across a curtain in just a few seconds might span hundreds of kilometers in altitude. This immense scale softens the appearance of motion, giving the aurora its unique blend of speed and stillness. Even with these scientific explanations, the movement of the aurora can feel almost meditative. Each shift in brightness or shape is the visible expression of processes that operate far above the surface, guided by forces that work quietly and consistently. The glow outlines the invisible structure of the magnetosphere, revealing motions that would otherwise remain hidden in the space surrounding our world. Beyond the soft drifting of ordinary auroras, there are moments when the sky brightens suddenly, as if a silent wave of energy has arrived from nowhere. These events are called auroral substorms, and they are responsible for many of the vivid motions people associate with the northern lights. Sudden ripples, fast sweeps of brightness, and bands of light breaking into rays. A substorm is not a storm in the atmospheric sense. It is a magnetic event occurring far above the Earth, shaped by the balance between the solar wind and the planet's magnetosphere. The process begins in the long magnetic tail behind the Earth, a region that stretches far into space on the night side of the planet. The solar wind pushes against the magnetosphere, elongating its field lines and storing energy like a drawn bow. Over time, the tension in these stretched lines increases. Eventually, the magnetic structure rearranges itself in a process known as magnetic reconnection. When reconnection happens, the stored energy is released, accelerating charged particles toward the polar regions and triggering the distinct brightening that marks a substorm. As these particles surge toward Earth along magnetic field lines, they enter the upper atmosphere in greater numbers than usual. The increased flow energizes oxygen and nitrogen atoms more intensely, producing brighter colors and faster movements. Curtains that were faint moments earlier may grow sharp and well-defined. Arcs can break apart into fine rays that rise and fall in quick sequences. The sky may appear to ripple as the incoming energy varies from second to second. Even though the motions can seem lively, they remain structured by magnetism, following invisible paths that guide every change in shape. Substorms typically unfold in 3 quiet stages. The first stage is the growth phase, where energy accumulates in the magnetotail as the solar wind pushes against the field. During this time, the auroral oval may darken slightly or shift position as the magnetic structure adjusts. The second stage is the expansion phase, marked by sudden brightening. This is when the most dramatic auroral movements occur. Light may race across the sky, spirals may appear, and regions that were dim may glow intensely. The final stage is the recovery phase, when the magnetosphere settles into a more stable shape and the aurora fades back into softer, more diffuse patterns. Substorms vary in intensity. Some are mild, producing only slight enhancements in brightness. Others are strong enough to push the aurora far from the poles, allowing people at lower latitudes to glimpse displays they rarely see. These larger substorms tend to occur when the solar wind carries magnetic fields aligned in a way that encourages connection with Earth's magnetic field. Once the connection strengthens, more energy flows into the magnetosphere, setting the stage for a more dynamic event. Despite their complex origin, substorms occur regularly. On many nights in polar regions, several small substorms may pass unnoticed by observers who are not watching continuously. Larger ones can be seen from hundreds of kilometers away. Each substorm is a release of magnetic tension, balancing the flow of energy arriving from the sun with the structure of Earth's magnetic field. While the sudden motions of a substorm might seem unpredictable, they follow a quiet logic shaped by physics. The colors, brightness, and forms all reflect changes happening beyond the atmosphere, in the magnetic space surrounding the Earth. When an aurora brightens in a swift, sweeping motion, it is the visible signature of distant magnetic lines, reconnecting and sending energy earthward. The sky becomes a canvas for these interactions, glowing softly with the imprint of forces that move silently above the planet. Seen from the ground, the northern lights stretch upward, reaching into the dark sky in long curtains and arcs. But from space, the aurora looks entirely different. Instead of rising above the horizon, it forms a glowing ring wrapped around the polar regions of the Earth. Astronauts aboard the International Space Station often describe the aurora as a soft, luminous band that circles the planet, curving in smooth shapes that follow the magnetic field lines far above the atmosphere. From this vantage point, the lights reveal their structure more clearly, showing how they form one continuous oval rather than isolated patches of color. The auroral oval appears as a thin, bright edge along the curve of the Earth. Its glow comes from the same collisions that produce the aurora on the ground, but from space, those collisions are seen from the side rather than from below. This angle allows astronauts to observe the vertical layering of the aurora, deep reds at the top, bright greens in the middle, and faint purples below. These layers stack gently above one another, creating a soft gradient of light that extends hundreds of kilometers into space. The thinness of the atmosphere becomes more apparent from this perspective, reminding observers how delicate the upper layers of the air really are. Satellites designed to study the aurora provide additional views. Instruments on board these spacecraft can detect wavelengths of light invisible to the human eye, including ultraviolet and infrared emissions. By mapping these wavelengths, scientists create detailed images of the auroral oval as it shifts, expands, and contracts. These maps show how the oval can widen during periods of strong solar wind or shift in position when Earth's magnetic field is disturbed. Some satellites also detect the energy of incoming particles, revealing how different regions of the magnetosphere contribute to the aurora's brightness. Another unique perspective comes from satellites that orbit above the polar regions. These spacecraft sometimes travel directly over active auroras, allowing them to view the center of the oval where the lights are strongest. From above, the aurora resembles a broad, glowing plateau rather than a sheet of light. The shapes that appear as curtains from the ground blend into smoother, more continuous formations when viewed from higher altitudes. This difference in appearance highlights how perspective shapes the way auroral structures are interpreted. The aurora can also be seen from spacecraft much farther from Earth. When distant probes or observatories turn their cameras back toward the planet, they often capture faint glows encircling the poles. These glows are visible even from the far reaches of the magnetosphere, showing how the aurora marks the boundary where solar particles enter the atmosphere. The Earth appears as a quiet sphere of light, with the aurora acting as a luminous halo that outlines the planet's magnetic architecture. Astronauts frequently describe the aurora as one of the most calming sights from orbit. The lights drift beneath the spacecraft in slow, gentle motions, following the same magnetic pathways that guide them when viewed from the ground. But in space, the aurora sits below rather than above the observer, giving the impression of floating above a soft, living glow. The curvature of Earth adds to this tranquil feeling, making each display appear as part of a larger, continuous pattern. Viewing the northern lights from space reveals how the aurora is not just a surface phenomenon. It is a three-dimensional structure that extends far above the atmosphere, shaped by magnetic lines that arc outward into space. The lights reflect interactions occurring across vast distances, connecting the Sun, the magnetosphere, and the thin upper air. From orbit, these connections become more visible, offering a peaceful reminder of how the Earth is embedded within a broader environment shaped by magnetism and energy arriving from the Sun. For centuries, people in northern regions have reported faint sounds accompanying the northern lights. Soft crackles, quiet snaps, or gentle whispers drifting through the air on still winter nights. These descriptions appear in folklore from multiple cultures, suggesting that observers long ago were sensing something more than just light. Yet for most of scientific history, the consensus was that the aurora was silent. The lights occur far too high in the atmosphere, often more than 100 kilometers above the ground, for sound created there to reach the surface. Sound waves travel slowly and require a dense medium, and the air in the auroral region is much too thin to carry audible vibrations downward. Despite these limitations, researchers began investigating reports of auroral sound more closely. In some rare conditions, sensitive microphones placed near the ground recorded faint acoustic signals during bright auroral events. These signals were soft and brief, sometimes described as static-like or similar to the quiet rustle of dry leaves. They did not match the timing or altitude of the auroral glow itself, implying that the sound was not produced by the aurora directly. Instead, the evidence pointed to processes occurring much lower in the atmosphere, close to the ground where air is dense enough to carry audible vibrations. The current leading explanation involves temperature inversions that form on calm, cold nights. A temperature inversion occurs when a layer of warmer air settles above a layer of colder air near the surface. This arrangement can trap electrical charges and allow them to build up in the lower atmosphere. During strong auroras, charged particles interacting with the magnetosphere may induce weak electrical changes closer to the ground. When the stored charges in the inversion layer discharge, they produce tiny crackling or popping sounds. These discharges are extremely faint, but in the absence of wind and noise, they can be heard by attentive listeners. Another idea suggests that the sounds come from electrostatic fluctuations caused by rapid changes in the geomagnetic field during strong auroral activity. These fluctuations could create minute electrical disturbances in objects near the ground, tree branches, dry grasses, or even clothing. Under perfect conditions, these disturbances might produce quiet sounds similar to static electricity. However, such events are rare and depend on a combination of atmospheric conditions that do not occur frequently. A third possibility is that some reported auroral sounds are influenced by psychoacoustics, the human brain's tendency to associate particular sensory experiences with imagined or internal sounds. When the sky fills with shifting, unfamiliar light, the mind may generate an internal sense of sound, even in silence. This does not diminish the experience. It simply reflects how perception combines visual and auditory information to create a unified impression of a moment. Even with modern instruments, the evidence remains subtle. No consistent, reproducible sound has been directly linked to the aurora itself. The lights remain a primarily visual phenomenon. The faint crackles or whispers reported by some observers likely come from secondary processes in the lower atmosphere, rather than from the aurora's true location high above the Earth. Whether the aurora is silent or not can depend on conditions that are hard to replicate or measure. What is clear is that the lights themselves do not produce sound in the upper atmosphere that can travel to the ground. Any audible signals arise from interactions much closer to the surface, shaped by weather, electrical conditions, and the sensitivities of the human observer. Understanding this distinction adds a quiet layer of clarity to the experience. The northern lights move in silence above the world, their glow shaped by collisions too high to be heard. Any sounds that accompany them exist only in the layers of air we live within, where the atmosphere is dense enough to carry gentle vibrations. The result is a phenomenon that feels both peaceful and mysterious, a light show unfolding above a landscape that listens softly below. Long before the science of auroras was understood, people living under northern skies created their own explanations for the shifting lights overhead. These interpretations were shaped by landscape, language, and the rhythms of daily life in cold, remote regions. Although the scientific view reveals the true origin of the aurora, the cultural stories offer their own quiet insight into how humans respond to beauty and mystery. Each tradition reflects a gentle attempt to understand something vast, using meaning to fill the space that science had not yet reached. In many Inuit communities, the aurora was thought to be the light of spirits playing or traveling across the sky. Some stories describe the lights as the reflections of departed souls guiding hunters or showing that the world above was active even in the coldest nights. These interpretations were not fearful. They carried a sense of companionship, as if the lights were reminders that life continued beyond the visible world. In a landscape defined by long winters and limited daylight, the aurora provided a quiet reassurance. The Sami people of northern Scandinavia approached the aurora with reverence. In some areas, the lights were considered powerful and should not be whistled at or pointed toward. Sudden movements of the aurora were thought to signal that the lights were aware of human actions, and people behaved respectfully in their presence. This gentle caution did not come from fear, but from a belief that the lights held significance beyond ordinary phenomena. The aurora's subtle motions encouraged observant, intentional behavior. In Finland, the northern lights were described in terms linked to animals. One well-known story tells of a mystical Arctic fox running across snowy hills so quickly that its tail brushed against the drifts, sending sparks into the sky. These sparks then rose to become the aurora. This tale reflects the close connection between northern cultures and the animals they depended on, weaving natural behavior into a quiet explanation for the sky's glow. Across Norse traditions, the lights were sometimes believed to reflect the armor of warriors or to illuminate paths traveled by spiritual figures. In some stories, the aurora was a protective fire shielding the world. Even though these interpretations varied between regions, they shared a sense of the aurora as something connected to movement, guidance, or strength. The shimmering arcs mirrored ideas of travel and purpose, shaped by the rugged landscapes and long sea journeys associated with northern life. In Icelandic folklore, the aurora was often linked to childbirth. It was thought that the lights could ease labor if the mother avoided looking directly at the sky. This belief blended practicality with symbolism. The aurora's calm brightness was seen as supportive, yet its intense movement was treated with caution. These stories gently balanced hope with respect for the unpredictability of nature. In East Asian records, particularly in ancient China and Japan, unusual sky glows were sometimes interpreted as celestial dragons or signs of significant events. although these interpretations were influenced by cultural symbolism rather than direct auroral familiarity. They show how people from distant regions tried to describe sky phenomena using imagery rooted in their own traditions. When rare red auroras were seen at lower latitudes, they often became woven into historical accounts as omens or markers of important changes. Indigenous groups in North America, outside the Arctic, also created interpretations tailored to their environments. Some communities described the lights as campfires of spirits, while others saw them as reflections of ancestral gatherings or dances. These interpretations emphasize connection between the living and the departed, between land and sky, and between the present moment and the broader continuity of life. Although these stories differ in detail, they share something gentle, an attempt to understand a quiet, luminous display using metaphors grounded in the experience. The aurora became a mirror for human imagination, shaped by the landscape and the emotional needs of each community. Today, the scientific explanation replaces the myths, but the stories remain part of the aurora's history, showing how people responded to a phenomenon that felt both peaceful and extraordinary. In exploring these interpretations, the Northern Lights become not only a physical event, but a thread woven through generations of observation and storytelling. Each culture added its own meaning, turning the sky's glow into something familiar and comforting, even before anyone knew the science behind it. Most animals do not react to the Northern Lights in the way humans do. While people often look upward in awe, watching the colors shift and ripple across the night sky, wildlife tends to treat the aurora as part of the natural environment. For many species living in high-latitude regions, the lights are a familiar occurrence that does not change their behavior in any dramatic way. The aurora is simply another part of the nighttime landscape, appearing without sound, scent, or physical disturbance, factors that animals rely on far more than visual cues when deciding how to respond. Creatures such as caribou and reindeer, which migrate across Arctic regions, move under auroral skies without altering their patterns. Studies using GPS tracking have shown that caribou do not change direction, pace, or resting habits during bright auroral events. Their senses are tuned primarily to wind, ground conditions, predators, and the availability of food. Because the aurora does not generate vibrations or smells and produces no significant change in illumination at ground level, it does not carry the signals these animals associate with danger or opportunity. Birds that travel long distances, including species that migrate at night, are also largely unaffected. Many migratory birds use Earth's magnetic field to help guide their navigation. This raised questions about whether auroral activity might interfere with their sense of direction. Experimental evidence shows that while geomagnetic disturbances can influence navigation under certain conditions, the visible part of the aurora itself does not typically confuse or redirect birds. Their magnetic sensing mechanisms respond to deeper changes in the geomagnetic field, rather than the light displays created above. Marine animals also inhabit regions beneath the auroral oval. Seals, whales, and fish experience the lights from entirely different perspectives, filtered through sea ice or deep water. The aurora's glow does not penetrate far below the surface, and any light that reaches the water is too faint to influence marine behavior. For these animals, The ocean provides a stable environment where pressure, temperature, salinity, and sound are more relevant signals than the faint shifting of light above. Some species, such as foxes, wolves, and Arctic hares, rely heavily on night vision. Although the aurora does produce visible light, it is much dimmer than moonlight and often comparable to the brightness of stars. Animals adapted to hunt or forage in darkness do not treat the aurora as a significant source of illumination. They continue moving through snowfields and forests with the same focus they would on any clear night. Observers have occasionally noted wildlife pausing briefly beneath bright displays, but such behavior appears to be curiosity rather than alarm. Owls and nocturnal birds offer another point of interest. These species depend on low light conditions for hunting, and their eyes are adapted to detect subtle differences in brightness. The aurora's light can cast faint shadows in extreme cases, but it remains too soft to disrupt hunting habits. Prey animals do not become more visible, and predators do not gain an advantage from the glow. The aurora adds a backdrop to the scene without altering the balance between predator and prey. The creatures that appear most affected are often those with social or vocal tendencies, such as dogs or domesticated animals brought into northern regions. Some dogs have been reported to bark or grow quiet during bright auroral activity. These reactions, however, seem to stem from human behavior, people stepping outside, pointing upward, or speaking in excited tones, rather than from the aurora itself. Animals respond to changes in their immediate surroundings far more than to distant atmospheric phenomena. Even though animals rarely react strongly, their presence beneath the aurora adds context to the environment. Herds move across frozen landscapes while green lights ripple silently overhead. Birds pass through the sky beneath faint curtains of red. Marine creatures surface in dark waters while the aurora moves above unseen. The lights become part of the same ecosystem, a quiet feature of the natural world that has been present for countless generations. In this way, the northern lights reveal something about life in polar regions. The environment is shaped more by cold, wind, and seasonal cycles than by the glow of the sky. For animals, the aurora is a gentle backdrop, a constant presence that blends into the fabric of their world, noticed occasionally but rarely treated as anything unusual. While the northern lights appear silent and distant from the ground, they form within a region of the atmosphere that plays an important role in global communication. This region, known as the ionosphere, lies far above weather systems and contains charged particles that reflect or guide radio waves. When an aurora forms, the ionosphere becomes more active. Incoming particles from the sun change the density and motion of charged atoms and molecules there, creating quiet disturbances that can influence radio transmissions, satellite signals, and GPS accuracy. These effects are subtle for everyday life, but they reveal how closely technology depends on the calm structure of the upper atmosphere. The ionosphere normally reflects certain types of radio waves back to the Earth, allowing signals to travel over long distances. This reflection depends on the density and arrangement of charged particles in specific layers of the upper atmosphere. During strong auroral activity, the flow of energetic particles increases the number of charged particles in these layers. This change alters how radio waves bounce or bend as they approach the ionosphere. Signals that normally reflect cleanly may scatter, fade, or shift in frequency. Radio operators in polar regions often notice these disturbances as quiet interruptions in communication. GPS systems also rely on the ionosphere. GPS satellites send signals through this region toward receivers on the ground. As these signals pass through layers filled with charged particles, they slow slightly or change direction in predictable ways. GPS devices correct for this naturally by using models of the ionosphere's usual behavior. However, during active auroral periods, the charged particles become more unevenly distributed. This irregularity causes the GPS signals to refract in ways that are harder to predict, leading to small errors in positioning. These errors are usually minor, sometimes shifting a signal by a few meters. But in areas close to the auroral oval, the effect can become more noticeable. High-frequency radio communication is especially sensitive. The wavelengths used by these signals depend heavily on smooth, stable ionospheric layers. When those layers become turbulent during auroral activity, the radio waves can be absorbed instead of reflected. This absorption can temporarily silence long-distance radio transmissions. Scientists monitor these changes using instruments called ionosondes, which measure how radio pulses travel through the ionosphere. Their data show that auroral activity can create pockets of disturbed air that move and shift with the lights above, shaping the quiet patterns of communication in polar regions. Satellite communication can also experience minor effects. When the aurora increases the density of charged particles around Earth, it raises the likelihood of signal scattering in certain frequency ranges. These disturbances do not damage satellites, but they can introduce small delays or fluctuations in data transmission. Modern systems are designed to compensate for these variations, making the effects mild and temporary. The magnetosphere also plays a role in these disturbances. When a substorm or strong auroral event occurs, magnetic field lines move and reconnect, changing the orientation of charged particles along their paths. These changes ripple into the ionosphere, altering the way it reflects and refracts signals. The resulting disturbances are part of a broader cycle in which energy from the sun influences both the aurora and the electromagnetic environment surrounding the Earth. For most people, these effects remain unnoticed. Everyday communication continues without interruption, and GPS navigation remains functional. Pilots, researchers, and polar radio operators may observe brief fluctuations, but even those are usually short-lived. What the aurora demonstrates is how interconnected the Earth's atmosphere and magnetic environment are with the technology humans use. A quiet glow in the sky reflects subtle changes occurring in layers of air that support global communication systems. In this way, the northern lights reveal more than beauty. They show that the upper atmosphere is active and responsive, shifting gently as particles arrive from the sun. These shifts create patterns not only of color in the sky, but also of small variations in the signals moving through the ionosphere. The result is a reminder that the atmosphere above us is both delicate and dynamic, shaping light and communication with the same quiet processes. While the northern lights capture most public attention, an equally vivid display unfolds around the South Pole. Known as aurora australis, the southern lights follow the same scientific principles as their northern counterpart. Particles from the sun interact with Earth's magnetic field, spiral toward the poles, and collide with oxygen and nitrogen atoms in the upper atmosphere. The result is a glow that forms in arcs, curtains, and spirals across Antarctic skies. Even though fewer people live in the far south to witness it, the southern lights are just as active, structured, and colorful as the auroras in the Arctic. The auroral oval in the southern hemisphere is nearly a mirror image of the northern oval. Both ovals are anchored to the magnetic poles rather than the geographic poles, forming rings of light that shift and stretch depending on the solar wind. When a burst of energy reaches the Earth, the southern oval brightens and expands just as the northern one does. Satellites often capture both ovals glowing at the same time, forming two luminous halos on opposite sides of the planet. These simultaneous displays show how closely auroras reflect the geometry of Earth's magnetosphere. Because Antarctica is largely uninhabited, aurora australis is rarely observed directly from the ground. The few people who do see it, researchers at Antarctic bases or travelers on southern expeditions, describe displays that fill the sky with wide, sweeping structures. The dry, cold air and minimal light pollution in these regions can make the colors appear sharper than in many northern locations. Under the right conditions, the aurora can spread across the entire horizon, shifting quietly as energy flows along magnetic field lines. Some of the best views of the southern lights come from southern ocean regions. Ships traveling between Australia, New Zealand, and Antarctica often pass beneath the southern auroral oval during strong solar activity. Passengers on these routes may see arcs forming above the water or curtains drifting along the horizon. The ocean provides a dark, uninterrupted backdrop that allows the aurora to stand out clearly, creating displays that can be seen even when the lights remain relatively low in intensity. Land-based observers in southern Australia, Tasmania, and New Zealand also have opportunities to witness aurora australis. These locations sit close enough to the auroral oval that strong solar activity can bring the lights into view. The displays at these latitudes tend to appear as faint glows or arcs near the southern horizon, though intense geomagnetic events can produce colors bright enough to fill large portions of the sky. These lower latitude sightings occur more frequently during periods of solar maximum, when the sun's activity increases. One subtle difference between the northern and southern auroras involves the magnetic environment around each pole. Earth's magnetic field is slightly tilted and not perfectly symmetrical. This means the southern oval can sometimes shift into regions where atmospheric conditions differ from those in the north. As a result, certain features, such as the height or brightness of specific colors, may vary slightly between hemispheres. These variations are minor and do not change the fundamental structure of the aurora, but they show how the planet's magnetic field adds quiet complexity to the lights. Satellite observations have provided much of what is known about aurora australis. Cameras aboard orbiting spacecraft capture the oval spreading across Antarctica, revealing patterns that would otherwise remain hidden. These views show that the southern lights are consistently active, producing shapes and motions that mirror those in the north. The two auroras respond to the same magnetic forces and solar conditions, rising and fading together in coordinated displays across the planet. Even though fewer people see the southern lights, they remain an essential part of Earth's auroral system. While the north offers visibility to millions of observers, the south carries the same beauty in remote, untouched landscapes. When both hemispheres glow together, they form a pair of luminous rings that wrap the Earth in a quiet symmetry, reflecting the shared magnetic structure that guides the lights at both poles. Most auroras drift quietly across the sky, shaped by ordinary flows of particles from the sun. But every so often, the sun releases a stronger burst of energy that travels outward through the solar wind. When these bursts reach Earth, they create auroras far brighter and wider than usual. These events are known as geomagnetic storms, and the strongest among them can produce light displays visible far from the polar regions. Although they attract attention because of their unusual brightness, the science behind them remains the same: charged particles guided by Earth's magnetic field into the upper atmosphere. The difference lies only in the intensity of the incoming energy. One of the best-known examples is the Carrington event of 1859, named after astronomer Richard Carrington, who first observed a bright solar flare linked to the storm. When the solar particles reached Earth, the auroras were seen near the equator in regions where they are normally never visible. People in tropical climates reported red skies that glowed throughout the night. Telegraph systems experienced electrical disturbances because the changing magnetic environment induced currents in the long wires. Despite these effects, the event remained primarily a natural light display, brighter than usual, but created by the same simple interaction between the solar wind and Earth's atmosphere. Historical records describe several similar events. In 1582, observers in Portugal wrote of red and white lights covering the sky. Chinese and Japanese archives contain descriptions of sky glows that stretched across large portions of the horizon. These accounts often mention unfamiliar colors or unusual brightness, which suggests that the events occurred during strong geomagnetic storms. At the time, people did not yet understand the connection between the sun and the aurora, but the descriptions align well with modern scientific knowledge of how energetic particles behave. Evidence of past solar storms can also be found in natural archives such as ice cores and tree rings. These materials preserve chemical signatures created when high-energy particles interact with Earth's atmosphere. By examining these signatures, scientists can estimate the magnitude of ancient events. Some findings suggest that Earth has experienced solar storms even stronger than the Carrington event, occurring hundreds or thousands of years ago. These storms would have produced unusually bright auroras, likely visible across much of the world. Their effects were limited to the upper atmosphere, leaving behind quiet markers in natural records rather than dramatic changes on the ground. During strong storms, the aurora behaves differently from its typical patterns. The auroral ovals expand, moving toward lower latitudes. The colors may shift, with red becoming more pronounced at higher altitudes. The lights can appear in regions where people may not expect them, over southern Europe, the central United States, or parts of Asia. These displays often create broad, gentle glows that fill the sky, rather than the structured curtains seen near the poles. This difference comes from the wider distribution of particles entering the atmosphere and the deeper disturbances occurring in the magnetosphere. Geomagnetic storms do not alter the basic physics of the aurora. They simply increase the amount of energy reaching Earth. When more particles arrive, more oxygen and nitrogen atoms become excited, producing brighter and more widespread light. The magnetosphere responds by shifting into a different configuration, guiding particles along paths that reach farther from the poles. These adjustments occur smoothly, reflecting how flexible and responsive Earth's magnetic field can be. Although extreme solar storms draw interest because they are unusual, they remain peaceful natural events when viewed from the ground. The lights continue to move in calm shapes, drifting across the sky with the same gentle presence seen in ordinary auroras. The scientific explanation behind them remains steady: sunlight interacting with the Earth's magnetic environment and upper atmosphere. Understanding these stronger storms adds context to the aurora we see today. Even the brightest historical events were simply amplified versions of the same quiet processes that create the familiar green arcs and curtains. They reveal that the sun's influence can vary across time, shaping Earth's skies with moments of enhanced color and reach, while keeping the basic nature of the aurora unchanged. Even though auroras are shaped by forces in space, their appearance can be predicted with surprising accuracy. Scientists monitor the sun, track the solar wind, and observe the magnetosphere to estimate when and where auroras are likely to appear. The process involves physics, mathematics, and continuous measurement of conditions stretching from the surface of the sun to the edges of Earth's atmosphere. While the predictions are not perfect, they offer reliable guidance about when the lights will brighten and how far from the poles they may extend. Aurora forecasting begins with observing the sun. Specialized telescopes watch for features such as sunspots, coronal holes, and solar flares. These structures reveal areas where the solar wind may intensify. When a burst of particles called a coronal mass ejection is detected, scientists can estimate its speed and direction. Instruments aboard solar observatories measure the acceleration of these particles and calculate when they might reach Earth. This is the earliest stage of aurora prediction, providing a broad estimate of activity several days in advance. A more precise forecast comes from monitoring spacecraft that sit between the Sun and Earth, such as the ACE and Discover satellites. These satellites measure the speed, density, and magnetic orientation of the solar wind as it approaches Earth. Because they sit about 1 million miles upstream, they provide approximately 1 hour of warning before the particles reach the magnetosphere. This short-term data allows scientists to refine predictions, indicating whether the incoming solar wind will strengthen the aurora or leave it unchanged. Once the solar wind reaches Earth, the magnetosphere begins to respond. Auroral activity depends heavily on how the solar wind's magnetic field aligns with Earth's magnetic field. When the two fields interact in a way that encourages energy transfer, particles flow more easily into the auroral zones. Scientists use models of magnetic reconnection and particle motion to determine how strongly the magnetosphere will react. These models are updated continuously as new measurements arrive, creating forecasts that are more dynamic than simple weather predictions. The next layer of prediction involves observing the ionosphere. Ground-based instruments such as magnetometers track how Earth's magnetic field changes during disturbances caused by solar activity. When the field begins to fluctuate, it signals the start of auroral movement. All sky cameras and sensitive light detectors in northern and southern regions record real-time brightness data, allowing scientists to identify where the auroral oval is strongest at any given moment. These observations help refine estimates of where the lights will be visible, especially for people living near the edge of the auroral zone. Mathematical models, such as the ovation model developed by the National Oceanic and Atmospheric Administration, combine solar wind measurements, magnetospheric physics, and ground-based observations to estimate the probability of seeing auroras at specific latitudes. These models update every few minutes, offering predictions about the shape, size, and brightness of the auroral oval. While the models cannot account for every variation, they provide a reliable map showing how far the aurora may extend during active periods. Scientists also use historical data to understand patterns in auroral behavior. The Sun follows an approximately 11-year activity cycle, with periods of greater activity known as solar maximum. During these times, auroras become more frequent and more intense. By comparing current measurements with past solar cycles, researchers can estimate general trends. Although the exact timing of individual events cannot be predicted long in advance, the broader pattern provides a quiet framework for understanding how auroral frequency changes across years. Even with advanced technology, aurora prediction retains an element of variability. Small changes in the solar wind's magnetic orientation can drastically alter the outcome. A strong burst of solar energy may produce only a mild aurora if the magnetic alignment is not favorable. Conversely, a seemingly ordinary solar wind stream can generate vivid lights if the alignment supports efficient energy transfer. Scientists account for this complexity by emphasizing probabilities rather than guarantees. Predicting auroras is a blend of observation, modeling, and continuous data collection. Every step reflects the interaction between the Sun and Earth, from the first sign of a solar flare to the arrival of particles in the upper atmosphere. The result is a quiet and thoughtful process that translates distant solar events into an understanding of when the sky will glow. For those who watch the predictions closely, each forecast becomes an invitation, an opportunity to look upward when the moment arrives and find the colors drifting gently across the night. Auroras are not unique to Earth. They appear on several other planets in the solar system, forming wherever magnetic fields and atmospheres interact with charged particles from the Sun. These planetary auroras follow the same principles as the northern lights, yet each world shapes the phenomenon in its own quiet way. Differences in atmospheric composition, magnetic strength, and rotational speed create displays that reveal something about the planet itself. Studying these auroras allows scientists to understand not only the lights, but also the environments in which they form. Jupiter produces the most powerful auroras in the solar system. Its magnetic field is more than 10 times stronger than Earth's, and it rotates rapidly, completing a full turn in just under 10 hours. These factors create intense electrical currents that guide particles along magnetic lines into the planet's upper atmosphere. Unlike Earth's auroras, which depend mostly on the solar wind, Jupiter's lights are shaped greatly by its volcanic moon Io. Io releases a steady stream of charged particles into space. These particles become trapped in Jupiter's magnetic field, feeding continuous auroras that glow day and night. Spacecraft images show bright rings near the planet's poles, along with distinct footprints where Io's magnetic connection touches Jupiter's atmosphere. Saturn also displays auroras, Though they differ from Jupiter's in both brightness and structure, Saturn's magnetic field is strong but more symmetric than Jupiter's, producing ovals that circle the poles in smooth patterns. The auroras shift gently as the solar wind changes, mirroring the dynamics seen on Earth. Because Saturn's atmosphere is composed largely of hydrogen, its auroras emit ultraviolet light that is invisible to human eyes. Instruments aboard spacecraft convert these wavelengths into visible images, revealing arcs and spirals that move slowly across the polar regions. Uranus and Neptune present more complex cases. Their magnetic fields are tilted significantly from their rotational axes and offset from their centers. This unusual geometry causes their auroras to appear in unexpected locations, sometimes far from the geographic poles. The interactions between solar particles and magnetism on these planets are less stable than on Earth or Jupiter, creating auroras that are faint and difficult to observe. Spacecraft have captured only a few images of these lights, each one offering clues about how magnetism behaves on planets with unusual internal structures. Even Mars experiences auroral activity, though it has no global magnetic field. Instead, Mars contains patches of magnetic crust scattered across its surface. When charged particles from the Sun interact with these localized magnetic regions, small auroras form. These lights do not appear in the same sweeping shapes seen on Earth. Instead, they occur as brief, concentrated glows in regions where the crustal magnetism is strongest. They also produce ultraviolet emissions, making them invisible without specialized instruments. The auroras on Mars highlight how even a fragmented magnetic environment can shape interactions between the atmosphere and the solar wind. The giant planets are not the only worlds with auroras. Moons such as Ganymede, which orbits Jupiter, have their own magnetic fields and can generate auroral activity. Ganymede's field interacts with Jupiter's in a complex way, creating small but measurable auroral patterns. These patterns shift depending on the Moon's position, offering insights into its internal structure and the composition of its subsurface ocean. Studying auroras across the solar system helps scientists understand more than the lights themselves. Each aurora reveals how the planet or moon interacts with the solar wind, how its magnetic field is shaped, and how its atmosphere responds to incoming energy. Some worlds create constant auroras, others produce faint, intermittent glows. Each display reflects a balance between magnetism, rotation, and atmospheric chemistry. These planetary auroras show that the interaction between magnetic fields and charged particles is a universal process. Even though the environments differ greatly, the underlying physics remains the same. The lights become a quiet signature of magnetism at work, glowing softly in upper atmospheres across the solar system. Whether seen on Earth, Jupiter, or a distant moon, auroras remind us that the same gentle principles shape many worlds, creating patterns of light wherever magnetic fields meet the energy of the Sun. While auroras can glow in red, purple, blue, and even pink, the color most people see, especially in high-latitude regions, is green. This green glow has a specific scientific origin rooted in the behavior of oxygen atoms high in Earth's atmosphere. The prevalence of this color reflects a balance between altitude, atmospheric composition, and the energy of incoming particles. Understanding why green dominates the sky during auroral events helps reveal the quiet chemistry that shapes the lights. Green auroras form primarily at altitudes around 100 to 150 kilometers, where oxygen atoms are abundant and the air is thin enough for long-lived emissions to occur. When charged particles from the magnetosphere collide with these oxygen atoms, they transfer energy into the atom's electronic structure. The excited atoms then release this energy by emitting light at a wavelength of 557.7 nanometers, which appears as a soft, luminous green. This wavelength is distinct and stable, making it a reliable signature of oxygen in the upper atmosphere. The air at these altitudes is dense enough for collisions between particles to occur regularly, but thin enough to allow excited oxygen atoms to emit light without being interrupted. At lower altitudes, molecules collide too frequently, interrupting the emission before it produces visible light. At higher altitudes, the air becomes too thin, and the emitted light may take longer to form, sometimes producing red auroras instead. The green wavelength appears in the unique middle zone, where the atmospheric density supports a steady, visible glow. Another reason green auroras occur so often is the energy level of the incoming particles. Auroral electrons typically carry enough energy to penetrate the atmosphere to the altitude where green emissions form most efficiently. While higher energy particles can reach lower layers and produce blue or purple auroras, those particles are less common. As a result, the conditions that produce green light occur far more frequently than those needed for more unusual colors. The brightness of green auroras also plays a role in their visibility. Human eyes are more sensitive to green wavelengths than to red or blue, especially in low light conditions. This sensitivity makes the green glow easier to detect and more prominent in photographs. Even when red auroras form at higher altitudes, the green layer below them may appear more vivid simply because of how the eye responds to different wavelengths. This does not diminish the red emission. It simply reflects the physiology of human night vision. In many auroral displays, green forms the base layer of the structure. Curtains of light often show a bright green lower edge, with other colors appearing above or below, depending on altitude and particle energy. The movement of the aurora can highlight this boundary as waves and folds sweep across the sky. The consistency of the green layer comes from the stability of the oxygen emission and the uniformity of oxygen concentration at those altitudes. Green auroras also appear more frequently because oxygen atoms in the upper atmosphere are long-lived compared to molecules of nitrogen. Oxygen can store energy for a brief period before releasing it as light. This slow release produces a steady glow that spreads across wide regions of the sky. Nitrogen emissions, by contrast, form quickly and fade rapidly, creating colors that appear only in specific conditions. The balance of these processes allows green to dominate the scene during most auroral events. Photographs of auroras often accentuate the green because digital sensors respond strongly to this wavelength. While cameras may capture vivid reds or purples during energetic displays, the green remains the most reliable and consistent color across all conditions. Even under lower levels of solar activity, when the aurora appears faint, the green emission may still be visible as a soft haze near the horizon. Understanding why auroras appear green adds depth to the visual experience. The color reflects a combination of atmospheric chemistry, particle energy, and the sensitivity of the human eye. Rather than being a simple feature, the green glow represents a quiet intersection of physics and biology, the meeting point between the behavior of oxygen atoms and the way humans perceive light. This gentle wavelength becomes the foundation for many auroral displays, shaping the familiar images people associate with the northern lights. Auroras appear to hang just above the horizon, but they actually occur far higher than any weather system or aircraft. Their glow forms in the upper atmosphere where air becomes extremely thin and where particles from the magnetosphere can strike oxygen and nitrogen atoms without frequent collisions. This region is part of the thermosphere and extends upward into the lower reaches of space. Understanding the altitudes at which auroras form helps explain their colors, their brightness, and the way they move across the sky. Most visible auroras occur between 100 and 300 kilometers above Earth's surface. This zone balances two important conditions: enough atmospheric density for particles to collide with atoms, and enough thinness for excited atoms to emit light without being interrupted. The lower boundary of typical auroras, near 100 kilometers, is where nitrogen emissions become more prominent. At this altitude, air is dense enough that oxygen atoms lose energy too quickly to produce green or red light. But nitrogen molecules can emit brief flashes of blue and purple as incoming particles strike them. Above this lower boundary, the classic green aurora forms. Between 120 and 150 kilometers, oxygen atoms can emit their characteristic green light efficiently. The density of air here is low enough for oxygen to hold energy for the fractions of a second needed to release it as light. This altitude layer often appears as the brightest part of a curtain or arc, outlining the structure of the aurora with steady color. Higher still, at altitudes above 200 kilometers, the air becomes so thin that oxygen atoms can store energy for longer periods. When they release it, they emit a deep red light. These red auroras form the faint, diffuse glows often seen above green arcs during strong geomagnetic activity. Because the emission process is slow, the red glow spreads over large regions without forming sharp edges. Its appearance signals that high-altitude oxygen atoms are interacting with the most energetic incoming particles. At the upper edge of the auroral region, around 300 to 400 kilometers, the atmosphere transitions toward the exosphere. Here, individual atoms are spaced far apart, and collisions become rare. Auroral emissions at these heights are faint and difficult to observe from the ground. Satellites, however, can detect ultraviolet emissions from oxygen and nitrogen at these altitudes. These wavelengths reveal patterns that complement the visible light seen from Earth, showing how far into space the auroral processes extend. The range of altitudes where auroras occur is shaped by the energy of the particles entering Earth's atmosphere. Higher energy electrons can penetrate more deeply, creating emissions at lower altitudes. Lower energy electrons interact higher up, producing red or green glows. The composition and density of the atmosphere change continuously with height, which is why specific colors form in distinct layers. Each layer acts like a quiet marker of atmospheric conditions, revealing how oxygen and nitrogen respond differently to particle collisions. From the ground, These altitude layers blend into a single luminous structure. Curtains and arcs often appear to stretch vertically across the sky, but this impression comes from the perspective of looking upward at a three-dimensional display. In reality, the layers are separated by tens or hundreds of kilometers. The sharp edges seen in some auroras correspond to boundaries where the particle flow changes rapidly. Smooth, diffuse glows reflect regions where the air is thin and collisions occur less frequently. Because auroras form so high above Earth, their shapes remain unaffected by weather. Clouds, storms, and atmospheric turbulence exist far below the auroral region. This separation explains why auroras remain crisp and steady, even during windy or unsettled conditions at the surface. The lights drift across the sky not because of air movement, but because of changes in particle flow guided by the magnetosphere. Understanding the height of auroras clarifies why they appear so serene. They exist in a region where air is quiet, where molecules are sparse, and where movement is shaped by magnetic fields rather than weather. Their glow forms at the boundary between atmosphere and space, reflecting interactions that occur in an environment untouched by the turbulence of the lower world. The result is a light display that appears calm and distant, shaped by processes that unfold far above the surface of the Earth. Auroras appear in many shapes, but the most familiar structure is the long, ribbon-like curtain that stretches across the sky. These shapes are not random. They reveal how Earth's magnetic field organizes the incoming particles and how the atmosphere responds at different altitudes. Each form, curtain, arc, spiral, or ray, reflects specific patterns in the flow of energy from the magnetosphere. By studying the geometry of these shapes, scientists gain insight into the invisible structure guiding the aurora. Auroral curtains form because charged particles follow magnetic field lines that run vertically through the upper atmosphere. When the particles reach regions where oxygen and nitrogen atoms can emit light, the glowing region traces the magnetic line. Since these field lines are grouped in sheets that curve toward the poles, the emitted light forms long, vertical structures. When viewed from the ground, these sheets appear as thin, waving curtains. Their folds and ripples depend on variations in the particle flow. Even slight changes in electron density can cause the curtains to shimmer or bend. Arcs, which are smooth, continuous bands stretching across the sky, reflect more stable conditions in the magnetosphere. These arcs form when the incoming particle flow remains steady and uniform. The shape arises because field lines curve naturally around the magnetic pole. As the flow intensifies, the arc brightens. If the energy shifts, the arc may break into smaller structures or fold into a curtain. Arcs often mark the boundary of the auroral oval, showing where the magnetosphere guides particles into the atmosphere most efficiently. Rayed auroras, where the light appears in tall, narrow columns, form when particles are funneled along closely spaced field lines with different energy levels. Each ray corresponds to a slightly different trajectory of particles. From the ground, these rays appear parallel, stretching upward from the horizon. In reality, the rays reflect how field lines converge at high altitudes. The spacing between them depends on subtle variations in the magnetosphere. When conditions change rapidly, the rays can pulse or flicker. Spirals and curls occur during moments when magnetic field lines become distorted by changes in the solar wind. These shapes reveal regions of twisting motion in the magnetosphere, known as Kelvin-Helmholtz waves, or areas where magnetic reconnection redirects the flow of charged particles. Spirals can form quickly and fade just as fast, appearing as gentle twists in an otherwise smooth curtain. Their movement reflects the dynamic interaction between the solar wind and the boundary of Earth's magnetic field. The appearance of complex shapes also depends on altitude differences. Green emissions usually occur at mid-altitudes, while red emissions come from higher layers. When these layers overlap, the shapes can look three-dimensional. A curtain might appear to glow red at the top and green below, creating the impression of depth. Spirals may seem to rotate because the dominant emission shifts between different altitudes as particle energy changes. Another factor influencing auroral structure is the presence of electromagnetic waves in the magnetosphere. These waves can modulate the flow of electrons, creating patterns of brightness along the auroral arc. In areas where the waves slow the particle flow, the aurora dims. Where the waves accelerate electrons, the aurora brightens. This interaction produces the fine-scale structure seen in many curtains and rays. The result is a pattern of light that seems to move with its own rhythm, shaped by processes occurring far above the atmosphere. Even with detailed scientific understanding, the shapes retain their visual softness. Curtains sway gently because the particle flow changes continuously. Rays brighten or fade as magnetic conditions shift. Spirals form and unravel as the magnetosphere adjusts to incoming energy. Each pattern reflects a balance between order and variation, a quiet interplay between structure and motion. From the ground, these shapes give the aurora a dynamic appearance, but the underlying magnetic framework is steady. The field lines act like invisible scaffolding, guiding every movement of the light. The patterns are simply the atmosphere revealing the pathways along which energy travels. In this way, the shapes of the aurora become a visual map of forces that would otherwise remain unseen, glowing softly as particles trace their steady paths into the upper air. As the lights of this topic settle, you can allow your thoughts to loosen and drift in whatever direction feels natural. There's nothing you need to hold on to, and nothing you need to follow. The images of color, motion, and quiet patterns can fade into the background, like a soft glow that stays only as long as it's welcome. The science behind the aurora will keep unfolding far above, steady and calm, whether you're waking or resting. You can let the rhythm of your breathing guide the pace of your awareness. Each inhale can widen the space around you, and each exhale can soften the weight of the day. If your mind wanders, it's simply doing what it knows how to do. You're allowed to drift, to pause, to rest without intention. The sounds around you can become quieter, or they can stay exactly as they are, without asking anything from you. The northern lights will continue to move in their own quiet patterns, shaped by currents of energy you never need to manage. You are separate from those movements, yet gently connected to the same calm principles that guide them. Steady flow, soft changes, and the comfort of familiar cycles. You can settle into that same steadiness now, letting the atmosphere around you feel safe and still. There is nothing more you need to hear tonight. You can let this space dim as you ease towards sleep, or simply rest with your eyes open, allowing the quiet to settle naturally. However you choose to end this session is enough. Sleep well, friend. Good night.